Okay. This is a continuation of the training on how we estimate stocking rate for the Akmala region in Kazakhstan using both field-based measurements and remote sensing products so that we can scale up field discoveries to a larger scale. And this allows us to do a much broader, large scale assessment of the country's stocking rate. For the last 2 weeks, Mark Wells and others have presented some of the fundamental theories or methods to estimate, stocking rate, then assess rangeland health, etc. And today, this is going to be a discussion and also presenting a method how to scale up field measurements to regional assessment of rangeland. And we are going to focus on the techniques, how to do that using remote sensing. As we said, I'm Jago Chi, professor at Michigan State University. I have been collaborating with Cas now and others, particularly back here with the scientists and the researchers in the US. Mark has been a long-time friend. I've been working with him for years, and I present this as a kind of a team work. I just want to make sure that we are representing, or this talk represent a collective wisdom of many people. And this is again funded by the ADB and Kaz, the Ministry of Ag in Kazakhstan. Let me see if I can get, okay. So what I want to do today is to present you two fundamental theories or the techniques of the remote sensing, and then move on to a scaling up, how we scale field-based measurements to larger scale. So the first set of slides, we call it remote sensing basics. And I want to maybe spend maybe 30 minutes or so to discuss, at least provide some of the information to you so that you know what that means and how we can use remote sensing to scale up the field-based measurements. And second part is really information for you, Earth observation systems and data. That is, where can you find the data we needed to estimate the stocking rate in your country, wherever you are. So those are the very fundamental remote sensing and observation systems. It's more for your information, and I put more slides than needed to just give you ideas and also references so that you can find more information later on. So it's a kind of a training package that we develop. Then I will focus on scaling up, the scaling up techniques. So that maybe we can spend 90 minutes or so, or maybe less than that. So it depends on how it goes. And I don't know if we want to take a 10 minutes or so break or not, but if you want to, just let me know so that we can make that arrangements. Okay, let me move on to the first set of slides on the remote sensing basics. Okay, this set, the first set of the slides is about what remote sensing is. Okay, so basically what you see here is a fundamental theory how remote sensing works. What you have here is the sun here, have this, we have a set, array of sunlights coming onto the earth, and you have a satellite to receive the reflected energy. And depending on what you have on the ground, and then the reflected energy would be different. And then that is a characteristic of what we have on the ground. If it's a vegetation, if it's a soil, or if it's a water, or if it's rocks, etc., the reflected energy will be received by the satellites. It's going to be different. So knowing different type of vegetation reflecting different proportions of the spectrum in the sunlight, of the sunlight, and we can determine what we have on the ground and what kind of maybe biomass or forage or other things we have on the ground. So this is the very fundamental one, okay? The major theory is that we measure the radiant energy. It's really a form of how light travels. If you just recall the diagram I showed earlier, then it is the physical characteristic of the surface that reflected different proportions of the radiant energy. So the radiant energy received by a sensor or a satellite is going to vary from time to time, from place to place, and also from wavelengths to wavelengths, different regions of that spectrum, okay? Here is something that you already know. Light travels both in the form of particles as well as in a wave form. So here is how we measure how the light travels. I want to show you that this diagram, that it has both horizontal and vertical polarization, and that allows us to measure light in different forms, different polarization. That allows us to detect or characterize the surface properties much more accurately. And the reason that we want to show this is that because it travels in the wave form at different wavelengths, it is sensitive to different properties of the atmosphere. So most of the time, we use what we call the visible and near infrared portion of the spectrum. And that is where we have less sensitive region to atmosphere. Otherwise, we'll be seeing very little reflected energy because atmosphere absorbs quite a lot in this and then in other regions. But there are very, very narrow portion of that spectrum that the sensors can basically receive energy. For example, if you go to this portion and very little energy coming through, but if you look this one, and the solar energy is much stronger, and then those are what we call the atmospheric windows. So you see those windows where we can see through the atmosphere and see the lights, okay? If you happen to design a sensor in the different portions like this, the absorption bands, we won't be able to see any light coming through. So That's why we select different, what we call different spectral bands or spectral readings, region where we are less sensitive to the atmosphere, okay? The fundamental terms we use is this: reflected energy, we call reflectance. Basically, how much energy the Earth's surface reflects off the target. Then also we use the transmittance. That means how much energy transmitted through atmosphere or through canopy. And those are very important terms in the remote sensing. And what we see or what we measure on the satellite sensors is this, what we call, reflectance. So that is the fundamental term that we measure on the satellite. That is a reflectance of the target, whatever the target is. Could be vegetation, could be soil, could be water, could be building, etc. Another term I want to point out is this, what we call absorptance. So basically, this is related to how much of the energy or sunlight being absorbed by plants. And that is the term or the energy that is converted to biomass or through photosynthesis. So very important three terms that we need to remember. What you see is this spectral reflectance on the, when we look at the satellite image. And then it is a characteristic of what we have on the ground in terms of how much energy or being absorbed by plants. So that's a very, very important one. What we'll talk about later is going to be primarily related to the reflectance, okay? So reflectance, as I said, is strongly depending on the photosynthesis. And of course, we know that if there is no vegetation, there will be very little or no photosynthesis. So photosynthesis is the process by which the sunlight energy being converted to a living, plant materials or biomass. That is absolutely the most important term. And when we talk about rangeland assessment, we talk about forage, talk about total biomass. It is derived basically from the photosynthesis. So that is very important term we need to remember, because we will be using that term a lot in the next few slides. The characteristic of the surface or the plants in reflecting the energy is such that the transmittance is high in this portion, but reflectance is, it's low, but the reflectance is high. So if you look at this curve, okay, and that is a reflectance curve, okay. And it also absorbs quite a bit here in different portions because of the photosynthesis process. So what we have here is whatever is in the middle, that is the total amount of the energy being absorbed. So if we see large absorption features on the satellite imagery, you will right away, you will feel that, oh, there are a lot of green biomass or green plants on the ground. So that is very important term we use, vegetation reflectance. And the term here reflects what we talked about, the reflectance, absorptance, and transmittance. Okay. When we look at the reflectance in different portions of the spectrum, in the visible portion, it changes quite a lot from 0.4 to 0.7. Here is 0.7 nanometer microns. Basically, it's a spectrum that reflects different portions of energy in the visible portion. And it depends on the chlorophyll concentration and others, but the most important thing is the chlorophyll. And that allows, that allows us to detect or measure, water and water quality and vegetation. So in the visible, it's very sensitive to those, characteristics of this surface. And then the absorptions by chlorophyll, and then of course A and B, is the fundamental thing that light interacts with the plants, and plants absorbs the sunlight energy to convert that into biomass. So here is what we need to know, the photosynthesis process. So chlorophyll, which is fundamental elements in the plants, and that is the fundamental property of plants that allows photosynthesis, allows sunlight energy being converted to biomass or to forage. There are other things that also reflects the absorbs the sunlight. So it's different elements in the plants. What I want to do is to skip some of those so that we know what so that we can focus on important things. For a larger pixel or for an area, you don't have a single plant, but you have a collection of different type of plants or soils and others. And in general, it is a function of how much of this vegetation you have on the ground, and also it depends on the status of the vegetation. So here is a green vegetation. You see that high peak in the green and then high reflectance in the near infrared region. But when you have the plants being dried or subject to water stress, if you have water stress, if you have, say, in the fall, the plants become yellow and then dry senescence, then they change the spectrum. So it goes, something like this. So when the vegetation becomes brown. So based on the shape of the curve we call the spectral reflectance curve, we can detect plants in different stage. And that allows us to estimate biomass, even if the plants are dry or senescent. Given the spectral characteristics of the plants in different spectral regions, the near infrared reflectance is very important. It has something to do with the internal leaf structures. It has total, it is dependent on the total amount of canopy biomass. This is a very important term. And we see very high reflectance in this region. Okay, this is reflectance curve here. And if a lot of vegetation, and you will see a lot of reflect a lot of much brighter reflectance or the much brighter images on the satellite sensors image. So here is a very, very important characteristic of the spectral reflectance, particularly in the near-infrared region. So those are the things that we use quite a lot to infer information from remote sensing. In general, this is a very healthy vegetation curve, and that is a very typical one, and that's what we use quite a lot when we teach classes to show that typical vegetation, healthy ones, reflect quite a lot in the near-infrared, and then absorbs here, and then very little reflectance in the in the short wave, like a blue or even in the green. So here is the red region, and this allows us to derive some of the information about the total biomass of the plants. And let me skip some of those slides, for the sake of the time, and I want to show you some of the important things that we will be using for today's talk. This curve shows that if you have an old leaves, new leaves, this older leaves could be much healthy or could be mature, but new ones could come up with fresh looking but then lower reflectance. So it's just depending on the growing stage, it may be different. And that allows us to even sense using remote sensing to sense the stage of the growth. Okay, this one I want to show you this. This is probably the most important thing. This one to me, reflectance in the near-infrared region. Okay, the higher the biomass, the higher near-infrared reflectance is. Okay, this is what we call the leaf area index. It is a kind of total leaf area per unit ground surface. So if you have a lot of leaves, and this number, the leaf area index, would be very high. And as you can see, when the leaf area index is 6, and you can see the curve is much, the reflectance in the near-infrared region is much higher. So by looking at the total amount of reflectance in the near-infrared region, we can quantitatively estimate the total amount of what we call foliage biomass, or total forage. One particular index is called normalized difference vegetation index. It's the one we use a lot. Many of you probably know this. So it is a way of measuring the difference between the reflectance in the near-infrared and those in the red spectral region. So if you look at the distance, and then you take the difference between the two, and then you normalize by the sum. That is the fundamental remote sensing theory of what we call the vegetation index. It's basically an index that is an indicator of the total biomass. Okay, and I want to show you a few things. What looks like for if we just have soils, how soil reflects energy and how water reflects energy. So soil reflects, sunlight energy very differently than the vegetation or than the plants. It depends on the soil moisture content, and also depends on the soil, the organic matter in the soil. So if you have very dark soil with a lot of organic matters in the soil, you will have different spectrum than the ones that had a lot of sand or a lot of dry sand, for example. And of course, there are other things that affect the soil reflectance, such as particle size and also the chemical content and the other things as well. So it depends on the type of soils, but in general, in Kazakhstan, we don't have much variation at large scale of the soil properties, but I think we need to look at, how the soil reflects the sunlight so that we can more accurately estimate forage, the biomass. That's what we need to do. But luckily, we have already had some of the remote sensing products that tend to avoid problems with the soils. So those are just soil reflectance as a function of organic matter or soil moisture, etc. So I will just skim through those, and of course you can take a look at this offline. This is not the focus, but I want to present this to you so that you know what looks like for different type of soils. So for different particle size and different surface texture, etc., and what look like on the satellite imagery and different type of patches. That's due to the difference in soil moisture and soil texture. Okay, and we also can and will sense or map water. So water reflects very little energy and is very dark on satellite imagery because low reflectance in the sunlight spectrum. And then once the light hits water, very little reflected in all other direction, but it's like a mirror. And only in this direction you see a lot. So most satellites are not what we call this a hot spot, or but most satellite measures lights reflecting in other, the vertical direction. So that's what we call nadir. Then, because very little reflecting in this direction, most is reflecting in this with the same angle as the incident angle. So you will see spot at a particular area, but the rest is very, very dark on the soil, okay? So anyway, so it absorbs quite a lot, very little reflectance in the water. So we'll map the water. And of course, it has transmittance and also absorptance, etc., but different spectral regions. I want to just to give you this idea of water being a special target in our research or in our effort, because we want to map out the the water to see where the water is, so that we can assess their accessibility to animals. Let me go get to the next portion of the what we call systems, what we the Earth observation systems, because we see that we can have satellite imagery reflecting the reflecting the properties on the surface, but what kind of surface products or remote sensing products do we have, and how we can use them to serve our purpose, okay? And I put a lot of slides here, but I think you will have that, for the future reference. And for the time being, I want to just to show you a few that I feel most relevant. to what we have to talk about today. Okay. Here is a list of satellite resources. You can go to those pages that allows you to download a lot of satellite, not only just a satellite imagery, but also a lot of products. Okay. Some of the products were derived from different type of satellites, and this is just not a complete set of the satellites, but it is a very most of the satellites here, that we can derive or we can use for our purpose. One of the most important thing is for our work, we use a lot of the satellite imagery measured by these two satellites. One is called Terra, and another one is called Aqua. And then those are the satellite names. And here are the sensors, okay, the sensors. So moderate resolution imaging spectrometer. This is the sensor we use a lot. And the data became available from 2000 until now, okay, till now. And the spatial resolution could be 250 meters, as small as 250 meters, and it could be large, aggregated to 8 kilometers. If you do a global research, and this could be the large scale, they could be, you could use the large, 8 kilometer to make sure that you don't run out of the computer resources. So anyway, there are other satellites available. For example, this one goes back to 1972. So that's as far as satellite data availability goes. And that the resolution is 80 meters. The 40 years of Landsat is probably most impressive satellite, continuous satellite measurements. NASA put a lot of energy. And if you are interested in high resolution data, and from 72 all the way to 2021, it is available. And then the Landsat 8 launched in 2013, still available. So it's a high resolution imagery or sensors that you can get the data in those areas. And here is the MODIS image snapshot, where on the globe you can get all the images for your study. Okay, this is the MODIS kind of footprint on the surface. The product we use here is this primary, we call it NPP. It's net primary productivity. And this is a product available from MODIS sensor, okay, MODIS sensor. And that has the biomass or forage information. And that's what we used for our project. And the data are available at 1 kilometer resolution. And then the product became available since 2000. So this is what we used. The NPP, you can go to the website to download the NPP and anywhere you want, but it is in the form of what they call tiles, basically mosaic tiles on the Earth's surface. So let me do the next session on the scaling up. So how do we scale up the remote sensing, scale up the field-based measurements to larger scale. So in the two sessions that we just introduced, we can have remote sensing imagery, and we can have remote sensing products that are fundamentally a measure of biomass or forage. And the question is, how can we scale up field-based measurements using those products, okay? So we have to rely on this data here, what we see, what we measured from the satellites. And then we have to rely on the field-based data that Mark and then other, a group people from, Ministry of Ag and COSNOW, et cetera, they measured. So then we can scale up to a region like the whole country or the whole obelisk. So that's what we, this method, the technique allows us to do, okay? So basically from the geospatial to regions the scale that is at obelisk scale, okay? So this is just animation, I don't know what happened. Okay, here is the methods we used. You have field-based measurements on different areas or different plots that Mark talked about. The people can do the transect or detailed field measurements in terms of the total amount of biomass, the composition of the species composition, and also the stage of growth, and then also the total, probably, we didn't measure, I believe, but the total nutrition value for different species, et cetera. And also we look at on the ground, how people manage their animals, like cows or horses, how many days they put on the animals in the ranch, and then is there any water, where the water is, and then also how much, the feeds do they bring to the animals in the winter time, etc. So all the information, we talked about, Mark talked about, will be available or it has been available, and that will be the fundamental information we collect on the ground. And then we use drone or high resolution satellite imagery to link the reflectance of those sites to the reflectance measured by satellite sensors. So that's why we want, the previous session, we talk about reflectance and also absorptance, and then also the transmittance, et cetera. We can only link reflected energy off the ground to satellite. Satellites do not measure biomass directly. It measures reflected energy, and reflected energy depends on the type of materials on the surface, or what type of surface, what kind of vegetation, what kind of plants, what is the proportion of the soil, et cetera. So that affects the reflectance. So once we know the reflectance of that particular pixel and that particular sensor, then we can establish the linkage between the properties of that pixel and the measured reflectance. And we do that with the drones, and also we do that with the satellites. So we basically measure the satellite reflectances from the satellite sensors, And depending on the type of the surface, we can estimate the total biomass, or NPP. That's what we're trying to establish the link. The linkage is the reflected energy. So from the methodological perspective, this is a diagram, what I want to present to you, how the methods work. Okay, so we talked about remote sensing imagery and from different sensors, of course, and then we can derive a set of product like the NPP. I showed you the NPP there, okay? And then the NPP, of course, is a function of the total biomass or forage. Other things we can also sense from satellites, like land use and land cover. So we need to know where the rangeland is or where the grasslands is. If it's urban, or it's agriculture, or it's water, or other things. So we can estimate those properties, or they map those classes using remote sensing, okay? And remote sensing can also sense the temperature and also precipitation, as well as the digital elevation in the model, the height, okay? We will talk about why those are important. They are part of the remote sensing product. They are part of the equation in the stocking rate estimate, because temperature could be used to determine the suitable climate or weather for animals to go out, or to graze in the field. So that could be a reason of one way to use the temperature. And of course, precipitation allows us to really estimate how much of the water falls on the ground and how much water might be accessible to the temperature, to the animals, etc. And then DEM is digital elevation model that could be used to determine where the animal can travel. They probably don't like to go very up high or on the mountains. Could be going to other flat areas, etc. So the slope could be an important factor to determine grazing range and where the animals go. So we can have biomass, and we can have all the things. We can determine number of animals. We can based on the field work, we can have this. And then we can use other parameters to determine the environmental, what we call the environmental adjustment. Basically, if you have high elevation or hot temperature or cold temperature, that affects the animal, the growth. So we have two functions. One is the environment. Another one is the biomass, or the range or the rangeland produced. Basically, it's a forage. Okay. So put that together, we use a geospatial analysis to integrate these two together to map the stocking rate, what we call the pixelized regional stocking rate. Basically, for each square area, for example, maybe 1 kilometer by 1 kilometer, we know how many how many animals we can put. So that's a stocking rate. So this is from the mathematical perspective, remote sensing imagery, satellite products, and then ground ground-based, methods that Mark, from the field work Mark and others, used, and then geospatial analysis to derive the information at each pixel. So how do we estimate the total, number of animals per square area? This is what I think Mark and others, derived or they, used from this work based on the USDA's method. And of course, this is a very traditional, recognized method. So the number of animals depends on several things. So this depends on grazing area. This is the GA, is total grazing area. So if you have large size of ranch, and then the total number of animals you can put should be large. So the total grazing area. And then AF here is available forage. So basically that's the total amount of forage that can be, fit, or the animal can, feed on forage amount, cows or horses can eat. So available forage per hectare. And of course, it's an annual production. So it's per year and per area and the total amount measured in kilos. That's the total available forage, okay? And then the D is the percentage adjustment for climate induced variation in production. So it could be, total of available forage, but what about this, potential drought or flood, whatever happens, that could be a factor. Some years could be low, some years could be high, and that is a weather adjustment. And then W is the water adjustment. It depends on where water is, and depends on how much, what's the distance between the, feeding stock and then the animal has to travel to get to the water. So sometimes you put the water nearby, the house, the ranch's house, and sometimes there are some natural water bodies that the animals can use, can get water from. So basically, it's counting for water distance, distance to the water animal can access. And then the S is, I believe, it's a slope. So it depends on, where, the topography, animals may or may not want to travel that far. It is an environmental factor that we need to consider. And then the other factor here is a DU, is days of use by animals allowed. As I said, in the first, just the slides that I used earlier. If the temperature is too low, the animals, maybe, we have snow and we probably can't graze anyway. So that is the number of days that you can, you can graze animals on the ranch. DFI here is a daily feed intake. So basically, it's the total amount of the forage or the biomass that animals take. So some large animals, the adult horses take different amount, and then and the cows take a different amount. So it's the daily feed intake, by animals. Here, the most important thing is what we determine here: the DFI, DU, and the distance, the drought, weather, etc. So can be estimated on the ground, but the only thing that is, measurable is the total amount of available forage. This is the available forage, okay, AF. The AF is measured by the total amount of, the NPP. It's above ground NPP, and then also related to the non-forage. So NPP is total amount of the biomass, but some of them are not eatable. So we are only talking about eatable, consumable by animals. So we need to take off the non-forage production, okay? So this non-forage standing biomass should be removed from the total amount of the biomass, okay? And then, so we have, this is the total amount of the forage available, but there is also another factor that determines, available forage. That is the grazing efficiency. Some of the some animals may not just consume everything, but they may leave something on the ground, or the part of that forage may not be, eaten, and then the grazing, they leave quite a bit on the, say, by the bottom of the plants. In that case, the grazing efficiency will be a little bit lower than 100%. In other words, it's not going to be just 100% of the forage being consumed by the whatever the either cows or horses, animals you have there. So this is where we determine this. So this can be determined empirically based on the experiences that we learned from other different places. And here, non-forage, depending on the type of vegetation we have, and then also look at the proportions of the forage versus the stems versus the scrub, etc. So that this proportion of the biomass that is not forage can be determined empirically or on the ground. So that is the term I believe we use based on the measurements we have from the 52 sites we measured in 2019 during the field work. So as you can see here, a lot of variables, the variables can be measured or estimated by on the ground, but the total amount of this biomass or the NPP is or can be measured by remote sensing. And that's where we can use the linkage between remote sensing and field measurements to scale up the stocking rate measurements. With that, we set up a practical or procedure to estimate the stocking rate. Okay, there are what I call 7 steps here. Step 1, you prepare input data, NPP. So in our case, we just visit MODIS website and then understand their products, the nature of their products, the accuracy, and also the methods, etc. So we download the NPP, the NPP products for Okamola region. We downloaded and we looked at the data quality and then look at the total amount of the land that is mapped as a rangeland. We eliminate others, other land cover types like a road or like urban, like water, etc. So we prepared the total amount of the NPP for rangeland only, okay? Then we determine the above ground NPP. So what is, when we know that the product NPP is the total amount, what is the percentage that is above ground, because animals cannot consume anything below ground. So the roots are in the under the ground and they are not available to animals. So that we need to determine that. And this is that is determined based on the field survey, So what is the proportion of that, biomass that is above ground? Knowing the species, that proportion is quite easily determined. And of course, Mark and others have the experience in determining that. Aside from that total amount of biomass above ground, and among the above ground biomass, there are non-forage biomass as well. So of course, this depends on the species and composition of the study areas. And based on the data we collected in the field, we can statistically determine or empirically determine what is the percentage of non-forage. So that's step number 3. Then we need to determine the grazing efficiency, and that is the information the team has got from the field survey in talking to the ranchers, and also to talk to the local people who know, what type of animals or they graze, sheep versus horses, or the cows or bulls, etc. So the sheep or maybe goat tend to consume quite a bit more, graze more aggressively on, than the sheep, or when maybe cow or the horses. So we determine the grazing efficiency, as I said, based on the field work or based on the experience. And then we determine daily feed intake. That is depending on the type of animals we take, we graze, and of course, it depends on it is from the field work or the site visit, and also depends on what type of animals and at what stage. It's a young calf or it's an old, what kind of animals we are talking about. So that is based on field work. And other factors that basically, like what we call, environmental factors, we need to determine. This is where the geospatial analysis comes in. So we compute or estimate distance from each pixel, okay, to the water. okay? So if you have a pond here, and then what is distance to the water or to the pond from different locations, from different pixels. So that factor was computed with geospatial technique and other satellite products. So for water, as I said, we have a water surface product that is available from the sites that I provided. So you can download that water product. Then we can calculate the distance to water from each pixel. And we assume that if the pixel is farther away, then the likelihood of animals travel to the water is low. But if it's closer and then that's easy access, then the animals could easily get access to the water, and then there shouldn't be any adjustment issues there. So we developed this kind of distance reverse distance function to determine how challenge or likelihood that animals would have to travel in order to access to water. And we also determine slope based on the DEM, okay? But we haven't got to the point where we have to make some decisions on the DEM because it is quite flexible, quite flat in Ocamala region. We put all the information, all the information from step 1 through 6 into a GEE Google Earth engine. We coded, we point to the product from NPP and water, etc., and then use the empirical or the field-based measurements of those parameters. And then we put in the code, we compute the stalking rate. Okay, so step 1, as I said, net primer productivity, I talked about, and then it is available there. Okay, so it is the total amount of the biomass accumulated over a year period of time. So this is just definition, and then you can use this term to get the meaning of what that means to understand why do we have to convert this to above ground biomass and then subtract that the non-forage biomass from this. So that this is give you the rationale. And here is the NPP website you can download, but on the GEE, you don't have to because the GEE in that environment, you can just point to the location where the NPP is. You don't have to download. That's the advantage of this, GEE approach. We have developed this code and we can share with you. And of course, you can modify, you can use it, and then you can do the calculation yourself. And of course, those the equations we built in the code were derived from the field measurements that the Casnow and the Agritech Hub and then Mark's group that we measured. So that needs to be considered. And here is just information about the NPP. Why do we have to account for total amount of biomass underground above ground and non-forage. I don't know, this is a little blurry. I think it's probably just because we translate into this into Russian. So you can see the total amount of how NPP relies on the GPP, the gross primary productivity, and is into different parts of the system. So, and step 2, determine the above ground or biomass. And how did we do that? And this is how we calculate. There are some of the methods and the theories we relied on, and some of the papers that people used. We use them as a reference. You can use those to make judgment in your work if the code we provide has different adjustment factors for above ground biomass, then you can use those references to adjust those numbers for your study area. And I assume that this is not, we use Alkamala region as an example, but if you are using the same methods in other places, you may want to consider, visiting or reading those references, make adjustment of what the above ground, how to calculate above ground biomass. Let me get some water. The proportion of the above ground biomass, what is the proportion of that? So we referenced some of this just for your information, and here is where the Kazakhstan is kind of area that we probably did, and then they are quite similar to this desert, and this is the steppe grass, along this kind of north and maybe around 30 to 45, 50 degrees north hemisphere. Okay. So this is the kind of reference we used, or at least for your information. I think Mark probably has used the USDA's number. In any case, I think it's quite similar. We used this in our analysis. Based on their work, it's about 35 to 39%. So that's what was used in Alkamala. Mark, if this is incorrect, maybe just come in and make a correction. But I think of course we can discuss about this. Step 3, determine non-forage. What is the total amount of forage? That it cannot be, I mean the biomass that is not forage. Okay. Some of the factors to consider. We considered for Alkamala, it was assumed to be 20% of the standing biomass is non-forage. This is based on the field-based measurements. Maybe if Mark has revised this number, we can revise in our case in the code. But other than that, I think we use this factor, 20%. Again, the factors that we need to consider in the non-forage, the term we use. So non-forage could be true for cow, but may not be true for goats, for example. Some of the animals can consume quite a bit of the, even off the stem, for example, that could be consumed. If that portion of being consumed increases, I mean, it depends on the type of animals, and this number could be different. So for the time being, we assume it is 20%, of the standing biomass is non-forage. The next step is to determine the grazing efficiency and GE.
G?
Yes.
No, you're absolutely correct. The original request for our team was to look at beef cattle and expanding the number of livestock from a beef cattle production standpoint. So all of our calculations on what is forage is based on our understanding of what beef cattle prefer to eat if they have free choice. And so if we are looking at mixed herd grazing, which is common in Akmola, and you were doing a ranch plan, then that 20% standing biomass would be, that's non-forage, would be appropriate for the number of beef cows in your herd. But we would have to adjust that then for if you had goats, it would be a different number. If we had horses, it'd be a different number, sheep and camel. And you can do that in our calculations because we do it by life form class of animal, both age and type of animal. So you would just adjust your forage percentage based on the life form of the animal and its age class. So but in all of our presentations and our final report to the Ministry of Agriculture, it's going to be on beef cattle. So we'll use a number that's somewhere around 20 to 25%. That'll vary a little bit depending upon where you are in the oblast.
Yeah, I think, Mark, our work is really a method, a method that can be applicable or applied to other animals or other, grazing system. We present this as a generalizable method. And this number, based on the type of animals they have, they can adjust that number to fit, to better fit what the purpose or what the situation, practical situation they have.
No, you're absolutely correct. I mean, and one example that we might use here would be cattle as a generic type of animal. But then we have two classes of cattle that are in Akmola and in most places around the world. You have your dairy animals, and then you have your beef cattle animals. So for a dairy animal, you would not want to have a pasture with a lot of mustards in them because the oils in the mustards, when they are consumed by the animal, doesn't really hurt the production or the life of the animal. But those oils then get into the milk and give a very bad off taste to the milk. And so you lose the value of your milk. So even within cows, we would have to separate between what is best for a dairy cow versus what is best for a beef cow to have optimal production and sale price. So you're right, very much, Chi, that this is a standardized way of calculating it. In stuff we'll be showing over the next two seminars, we'll show how to adjust it then based on mixed herds or a single species.
Yeah, as we discussed earlier, this is just for beef cattle. That's what we target. We were, in the very beginning, and this is, scalable to other, ranch type of animals as well. We use cows and dairy cows as example, but can be, adopted. The method can be adopted for even for camel, for example, for other animals.
And that would be our methodology for calculating forage demand by animal is usually based on what we call an animal unit equivalent, which is a biomass of the animal.
Mm-hmm.
And so there are adjustments then even for antelope, which do occur in Kazakhstan, or the wild horse. So we have a wide range then of what grazing animals, if we want to address, that can be done with this approach.
Yeah, exactly. So this is, as I said, maybe we should emphasize this is the kind of method, to general methods, and it's adjustable to other. We use the cow as an example, but it is applicable to others so long as we know those characteristics or of the animals, and we can adjust this method to fit for those purpose.
And probably the last and one of the most important things that we can convey to our audience is that these numbers that Chia is showing you, they're not static and they're not permanent. And so the stocking rate for sustainability is going to change on an annual basis. And that's why he was talking earlier about a drought coefficient. So we can calculate this now, and the approach we're taking is a conservative one, acknowledging that there's been, over the last 20 years, quite a lot of interannual variability in precipitation and temperature, and that translates that directly into how much vegetation is growing and the type or species that may grow. You may have more forbs if you have a wet year than other years. And so this is a general starting point. And then each year you may need to make adjustments in your herd depending upon the prevailing weather that is occurring that year.
The weather-related factor needs to be adjusted, annually, and depending on the drought, the precipitation, for example, there could be high, it could be low, and also a variability. And even if the same amount of precipitation, it depends on the pattern of the precipitation. Could be the forage could be different. So the weather adjustment factor needs to be considered. Another thing, Mark, and the audience in general, is this, we assumed that the species composition is more or less the same across the, Alcomola. That may or may not be true. So for each pixel, in theory, we should consider for each pixel of different composition, but we just don't have enough data to get that information for each, for everywhere. But the general assumption is that, the 52 sites are representative of general situation of the Alcomola region. That's where we use those parameters or the adjustment factors. So for all the pixels, they are the same.
Correct, Chi. And as you go south in the country and you get more into the desert environment, then if we were to apply this from a national perspective, we would have to have some calibration data down there around Almaty, or if we go over towards the Aral Sea, because you have different soil textures or soil colors for that reflectance, and you're going to have different species which will have different reflectance. And so the hardcore numbers that we're producing now are relevant for that northern grassland steppe communities and the different oblasts up there. But they'll have to be adjusted from a national perspective as you go south and you get different colored vegetation because of the shrub that start to dominate down there. And then as you get lighter soils towards the Aral Sea, again, we're going to have to make a different adjustments there for reflectance.
So true. And that's why we consider all those factors, to be figured into the equation, and we need to adjust them depending on the location and the year, and also the species, the information available to us from different field work. This is the grazing efficiency. We need to consider that as well. That is how much of the the plant tolerance that we have, and some of the plants have very low tolerance, as we just talk about this. If you move to other regions and then the different species, and they can be grazed to even maybe to the bottom, to the very root, maybe still survive, but the other species that may, if you consume, the animals consume all the leaves, and they may not survive next year. So it depends on what is kind of a species that you have on the ground, and you can determine the grazing efficiency. I think we assumed that they are constant across Acomola region in this case, and that the tolerance, the efficiency is, I don't remember exactly, but I think we have a code in that to be part of that equation in the GEE. I think here is the efficiency, the 35%. I'm not sure if this is a number that we used for the general area for the Eurasia, but for Acomola, this is assumed to be 35%. I think, Mark, maybe this is you derived from the or estimated based on the field work, or the look at the species and look at the literature and look at what the most optimistic or the probable number for the Acomola region. The reference that you cited provide the rationale, I believe, to use that 35% of grazing efficiency.
Yes, Chi. What we did was we took a very conservative approach, because once you have degradation, it's hard to recover from it. So if you're looking at greatly expanding the livestock production from beef cattle across this oblast, we wanted to start with a conservative value. We chose 35% of annual productivity, above ground productivity, as grazable forage. And then with time, if you're monitoring your rangelands and you find that that was too conservative, and change that up to 40%, or to the maximum would be actually change it back up to the 50%. What they used to say was take half, leave half. So we started conservative, because you can always expand your herd easier than you can to decrease your herd from an economic standpoint. And also then it minimizes the opportunity for having to deal with degradation. So it is in the literature, and that accounts for then what we don't know, and that is grasshoppers or locusts. They do occur in Central Asia, as well as other herbivores, ants, and what we call pikas, or groundhogs, and even the wild antelope. So we started conservative with the thought then that we could increase that value up to 50% based on science of monitoring the area.
it would be good that they know this, it's a very conservative approach. We don't want to overestimate, and we don't want to, degrade the land, what that is already being somehow degraded.
Yeah, and so from the very beginning, the concept that we used was a conservative approach. And so that's why in our calculations Chi was talking about, you have a discount value of forage availability. If your distance to water is too great, then those livestock really won't hit that outer edge of your pasture unless you force them to. And that'll have repercussions on animal health and energy gain. So they will tend to concentrate around watering holes. So we discount forage if they have to walk too far to get to water. If the slope is too steep, now that is not a problem in Akmola. But in the country, you do have mountainous areas where you have some very steep slopes. Again, the cattle will tend to avoid those steep slope areas in an open pasture. If they have a choice, concentrate on the flatlands and again, overgraze. And then, as I mentioned before, you have the uncertainty of interannual variability in precipitation and temperature. So we built in a reserve function, which we called a drought coefficient, so that if you do start into a dry period, you would have somewhere between 25 and 40% extra forage available from a normal year to shift into, because these C3 grasses retain very good energy and nutrient capabilities when they're dry. So if you have a low production year, last year's standing biomass still has value for a forage resource. So it allows you to get into that drought, determine that it is occurring, and destock in a rational manner so that you're not hitting the bottom of the beef market if your markets operate like they do in the United States. When we have a drought and it's finally recognized as a serious drought with very low production, then a lot of people will either buy hay to keep their herd, which gets very expensive, or they destock and sell to the feedlots. Well, if everyone's selling to the feedlots, the price drops. So we built in several mechanisms then to account for uncertainty to hopefully make livestock production stable from year to year.
Yeah, I think in the this is kind of conservative estimate, and then when the decision makers, the managers, or even the officials making decisions, they definitely need to consider this. The good thing is that we considered all the things together, and they can have some flexibility in ensuring, the market, accessibility, and also the drought and other factors. So this built in some of the flexibility, and that is what we intended to do, right?
No, you're absolutely correct. I mean, it's been built into the program. And as we report out to the Ministry of Agriculture and Asian Development Bank, we'll show them how there are these different kind of circuit breakers put into our calculations so that they have some flexibility in how they manage or oversee whatever policies they want to implement.
Mm-hmm. Yeah, and just flip through the next step, and we have a total of 7 steps. But this is, another step that we need to. This daily feed intake is another thing, Mark, we need to consider. Depending on the type of animals we put there, and also the age, is young or adult, etc. So this is again depending on how we manage, the rangeland system, and that the default is. This again, I think it's 13.6 kilos per day. That's kind of an animal daily intake. And this could be, again, different for different animals, and also from maybe, even for different environment. If it's very hot or very cold, that could be also a factor too.
No, and there is a table that we provide for the animal unit equivalent. So as I said before, it's based on total biomass. And we use in the United States a 1,000 pound animal, which is about 440 kilo mother cow. So if your base animal in your herd weighs more, then that daily feed requirement is going to go up. We show you how to calculate that. If your animal base weight is lower than that, then you reduce the feed requirements. And that's how then we basically make the calculation that 5 sheep are equal to in weight and forage requirement in kilograms per day as one mother cow.
Mm-hmm.
And then as the calf ages, and once the calf gets over 4 months, they start actually grazing. So then we have calculations for the calf, and every 2 months as that calf continues to graze weight, if you're really fine tuning your equations, then you would increase its forage consumption in a linear mass, in a linear distribution going upwards in relationship to its mass. And that's why we have, and that's why a bull here has a much higher daily use requirement, because they typically weigh substantially more than a mother cow. And a horse, if you have large horses, they would be close to what a bull would require on a daily basis.
Basically, it's the idea is that we built this function into this method so that managers, ranchers can adjust those numbers based on what they have, and on their ranch, and also the type of how they manage it as well. So we have this dynamic range of 1.4 to 19 kilos per day. That depending on the age and also the species, I guess, and that could be it is an adjustable number. We want to emphasize that in the estimate, across Alcomola, we use 13.6 kilo per day as a kind of default number. But again, this could be different. Depending on, for different ranchers and different animals. So once we have everything here, this is kind of a summary, okay? How we calculate everything based on this equation to arrive at a number of animals. As a final number or final variable of stocking rate. In the step 6, this is where I think we probably need to do a little bit more, validation, I would say. Basically, it's an adjustment for environmental factors, the distance to water, for different animals or the different species, different age, etc. So that distance traveled to the water could be different depending on what I said, depending on the type of animals. Some horses maybe, can travel a little, or cows or bulls can travel long distance there, and also, of course, it depends on the slope as well. So in the equation, okay, we did not consider DEM as a factor because it's, Alcomola is pretty flat. And for the distance, I think, Mark, we had a table to adjust the, with the distance at certain distance animals travel, and then further than that, we kind of prohibit the travel, even though animals may in reality travel further distance than what we had in the table, but our estimate is more conservative.
Yes, there is a table that we have in the documentation that has both slope and distance to water. And yes, I have seen animals grazing 60% slope lands. But in reality, what you see then if you stand back is the animal does not walk straight up the hill. It goes in a zigzag manner up the hill. And over time, that creates terraces, as we talked about in the first presentation, that really degrades the landscape. And so, yes, they can graze it, but it is not desired and it is not ideal for your landscape. And the same thing for water. Mm-hmm. Yes, animals will travel whatever distance they need to get to water, but you start impacting their health and their reproductive potential, and you really start stressing if they're carrying calves and their milk production, if they're being dehydrated during the day and then trying to refresh with water, there are herd health issues, and also then trailing issues where you start getting linear features to the landscape that open up areas for invasive plants. So we have a table then that we use within the USDA here then on distance to water. And we start discounting then how many cows you should have out there as that distance starts increasing, because you're not going to uniformly graze your area. They're going to concentrate in very specific areas.
Yeah, basically what I understand is that this project, the numbers we use, the environmental factors and distance and others, is basically a kind of ideal situation where we would like to see the managers to make this decision that are kind of conservative and also not to damage the environment. And the ideal kind of maybe it's not really optimistic, but it's a kind of ideal situation for as a stock and weight estimation. Next one is this is how we made the determination of that distance, and then we had a table. And then initially we thought, Mark, I don't believe we implement this in the code, but I think Linda is on the call, so she can explain this. Maybe, initially we thought it would be a function. It's not a linear function, but it's a kind of reverse distance. And this is something we suggested. And then also, the information we got, maybe needs to be validated. The distance to water availability was from satellite imagery as well. So once we have all the information, the coefficients or factors, and then above, below ground biomass, and then non-forage, and then also the type of animals, the forage use efficiency, etc. So everything we need to have in order to have that in that equation, we have them coded in the Google Earth engine. And that is where we run this. But I think one thing, when we run the Google Earth engine, you can run that with other program as well, like a Python or, the IDL, whatever. I think, for Kazakhstan, you have your choice. And it's very easy to convert from one, type of code or language, a programming language, to another. So I listed that maybe, that's the Google Earth engine tutorial. And Linda, are you on? Maybe you can just,
yes.
kind of, okay, maybe you can just, go through some of this, because this is what we have here. the equation we used, all the coefficients I estimate, I'm going to put it here and highlighted, in the red, and then they were coded in this GEE. So do you want to go ahead and explain what the GEE is and then how you did the calculation?
Yeah, sure. Can I have the authority to share my screen?
Okay,
so that I can take control of the slides.
Okay, sure. You can, let me end mine. Gunas, can you give Linda the authority to, to show, to share screen?
Okay, I'm working on it. Actually, she can share it. Linda tried it right now.
Okay, yeah, she can share.
In this project, we use the Google Earth engine to do all the calculations and the computations.
Linda, can you show the slides rather than just the flip through, the make presentation?
There. Oh, I'm showing the slides. Did you see it?
Now we just saw it. Okay.
Okay. Yeah. Hello everyone. So in this project, our group chose to use the cloud-based Google Earth engine to do all the calculations and the computations on the estimation of the stocking rate. What we are following is all the equations and the algorithms just explained by Dr. Qi and Dr. Weiss. So why did we choose the Google Earth engine? This is because it is cloud-based and very user-friendly, and most importantly, it is a highly computational platform, which is supported by Google Cloud Service. And by using the Google Earth engine, the users no longer need to spend a lot of time to download the data or to do any pre-processing of the satellite imageries, because the Google Earth engine itself already provides you the planetary satellite products, and it provides you the powerful APIs, including the Python APIs and the JavaScript APIs, which can allow us to do any geocomputational analysis that we desire. So in the Google Earth engine platform, we choose the remote sensing product to calculate the stocking rate. First, we choose the 500 meter NPP MODIS product from 2001 to 2019. Actually, we have the 1 kilometer product. We also have the 250 meter product. However, this one with the 500 meter spatial resolution is the best because it has a higher spatial resolution than the 1 kilometer one. And compared to the 250 meter one, this one has a better reliability due to some systematic error in the 250 meter satellite product. The MODIS team already called back that kind of product. So here we just keep on with the 500 meter product. And for the land use land cover map, we use two different data sets. The first one is the 500 meter MODIS annual land use land cover data at a global coverage. And the second one is the 100 meter Landsat, 100 meter land use land cover product released by the European Space Agency. And this one is from 2015 to 2019. And we also use the Landsat-based 30 meter resolution water product, which is also an annual product at a global coverage from 1984 to 2018. It provides us the seasonal and permanent water coverage at monthly scale and also at annual scale. And for the elevation, we use the SRTM 30 meter product. This product has already gone through the void fill process, so the reliability and the accuracy of the product is good to be used. And so here, what I want to show is that the steps, how we, the step-by-step tutorial that how we do the calculations. So first, if you click on this link, you can go to the first version of our Google Earth Engine code. And because we are, you know, putting efforts on this project, so we are improving the code. And later I will send out the latest version of the latest code. So here, let's take a look using the Google Earth platform itself. So first, we have the farms, the 52 farm set that Mark's group visited and did some field work. And also we have the Akmola Oblast administrative boundary, which can help us to define the study area of this project. So the first thing we need to do in Google Earth Engine is that we put these lines of script to help load the study area boundary and to load the farm set. If you click the run button, it will show the result in the lower part of your screen. Let me check off some irrelevant image. So here you can see the boundary of your study area and the points of interest. And then the next step, we want to calculate the number of animals first at the entire oblast level, and then we will refine it to the rangeland level. So as I mentioned before, we are using a 500 meter MODIS dataset. This one is very comprehensive. It's from 2001 to 2019. So we filter the data from the first date of 2001 to 2020 when we write this code. And because this is an image collection, for the image collection, they will have different bands. And we choose the NPP bands, which is what we really want in this product. And for each of the image in the image collection, we clip the image to the study area, or we extract the image from the study area. And in order to make sure it's a time series, we also set the system time to the image. So here we obtained the NPP product we need for the future calculations. And because of the MODIS group, when they produced this NPP product, they multiplied all the numbers by 10,000 for some computational purpose. So we need to convert it back to the real number. That's why we multiply each image by this scale factor. And then because the original unit of the NPP product is kilogram carbon per square meter, we want to convert it to the gram carbon per square meter. So we need to multiply another scale factor, which is 1000, and also set it as a time series. So by this step, what we have right now is that we have the NPP product from 2001 to 2019 with the unit of gram carbon per square meter. And then we want to calculate the available forage, which is short for AF. And according to the equations, we know it equals to the annual NPP minus the annual non-forage NPP times the grazing efficiency. And we also know the grazing efficiency is 0.37, and the other conversions to the NPP. So this equation can be finally converted to this equation, which is available for forage equals to 0.1036 multiplied by the NPP. And also we want to convert the unit to the kilogram per hectare for public use purpose. So we followed the rules by IPCC and use another scale factor of 20. So in this step, what we have is that we have all the available forage images from 2001 to 2019 in the unit of kilogram per hectare. And then we need to calculate the stocking rate. So here, again, if you remember the equations, the number of animals equals to the grazing area multiplies available forage divided by the final result of the days of use allowed and the daily feed intake of the animals. And so by doing some mathematical calculations, what we have is that for the number of animals in a pixel unit, here it's in a pixel unit, not in hectare, because we want to show it on the map. The final conversion factor is 0.00875. So by this step, we get the final estimation of stocking rate at a pixel level, which is 500 meter multiply 500 meter, and from 2001 to 2019. And if we want to take a look at a specific year, for example, the year 2017, we can, convert because currently this number of animals is an image collection. We can convert the image collection into a image list, and by pointing to the index number, we can get the specific year. For example, for the year 2018, the pointing index is for the year 2019, the pointing index is 18 because the index starts from 0 to the total number -1 of your image collection. And we can display the result on the bottom part. For example, here we have the number of animals for the entire oblast of 2019. And then what we need to do is to just focus on the rangeland part. So how did we choose the rangeland? First, we combine, as I mentioned before, we combine this 100 meter land use land cover images with the 500 meter modest land use land cover images, because the more land use land cover product we involve in this project, it can help to increase the final reliability of the rangeland determination. So for the 100 meter land use land cover map, what we use it is that we use it to help eliminate those pixels that were wetland. See here, these are waters, rivers, and they have wetlands here. But in the modest product, the modest team misclassified those pixels into rangeland. So we want to use the 100 meter land use land cover product to determine the misclassified pixels, including the wetlands, the woods, some woods, and from the modest product. In the modest product, they have a specific land use land cover type that can be taken as the rangeland. So these blocks shows how to do the determination of the rangeland. For example, so here we get the wetland pixels and other misclassified pixels, and here we have the rangeland pixels, including the misclassified pixels. By eliminating the misclassified pixels, we have the final map of the rangeland in the observed by the satellites in the Akmola Oblast. So since we get the range, the spatial cover of the rangeland, we can multiply this mask with what we have at the entire study area. In this case, we have the number of animals. Let's see, it range from the lowest number is 0.26 with the highest number to 10.1 for the rangeland. And then we want to take in consideration to the other environmental factors such as the distance to water and the slopes. So we include the water image also from 2001 to 2020. Actually, it stops at 2018, and we find the permanent water and the seasonal water. You can see the permanent water is the dark blue one, and the seasonal water is this light blue ones. And we also calculate the distance to water, which I forgot to show here, but we have the image in the slides. And then let's focus on the elevation part. So we have the 30-meter spatial resolution elevation image for the extracted for the entire study area. It changed from the -8 meter to approximately 900 meter. And we also use the slope function to calculate the slope of the entire study area. And according to our calculation, most of the region, they have the stiffness of the slope smaller than 15%, which is a threshold in our calculation. And only some pixels here are at a very relatively large slope scale, but actually we don't care about these slopes because it was, we don't care about those pixels because it was already masked out from our rangeland selections. Again, we have separated the blocks and did the detailed explanation in other slides, and all the results can be seen in the following slides. Dr. Qi, do you want me to
just go ahead and show the
Okay.
some of the images, the example we produced. I think we can stop there after that, and then we can have some questions.
Okay, sure. Let me go quickly through the images what we have. So we have the land use land cover maps at 100 meter, also at 500 meter for the entire country and for the interested study area. And we have the elevation map for the entire country as well, and also the study area, as you just saw from the Google's engine. And we have the precipitation of the entire country and also the study area. And the water mask map, like I just showed before. And this is the distance to water. The higher, the larger the distance is. So, for the slopes, we also have the numbers of the number of slopes for each pixel and the adjustment. and we combined all those factors together and include them into the equations and get the final result. So like, for example, we have the NPP, here is a typo, it's actually from 2001 to 2019, the 19-year maximum NPP value and the 19-year mean NPP value and the 19-year minimum NPP value for the study area. And then we did some estimation on the standing biomass also from 2001 to 2019. The image will be updated later. And then we have the stocking rate estimated using the equations and the factors we have. And we also reclassified the stocking rate images into different groups from the optimal to marginal groups to show how the suitability of different areas of the oblast for breeding the cattle. Yeah, I think that's all for my part. I will pass it to Dr. Qi.
Thank you. I think we can, yeah, I think we can, let's see. We can stop here, and then I'm sure you have questions and then, you know, maybe comments, etc. So I'm going to just get to the last portion of the, okay. Here is the last, slides I want to show, to put up there. And then basically what we did was use the field-based equation or the parameters or the factors we derived from the experiment, from the survey, as well as the publicly available data, and put in the Google Earth engine and then computed the stocking rate. And of course, there are factors that we made our assumption, as you heard the discussion with Mark and Linda present the GEE. So that's the kind of what I called a standard steps that we followed. And you can also follow the steps, use the code to do the the stocking rate calculation for your particular location or for your particular time period. So again, this is a method training, so that it's not just everything we said is correct, but I think the numbers could be adjusted and according to your practical situation or environment. And this is what we presented. In the next maybe 30 minutes or an hour, whatever it takes, maybe we can open up for questions.
Доктор Чи, здесь задали вопрос, Рашид Искенов. Какое оптимальное расстояние до воды должно быть на пастбище?
If we look at the table, if it's within, I think within certain distance, I don't remember exactly, maybe, let's see. Then it's 100% of this here. So if the distance within 1 kilometer, no need to adjust. But if it's longer than 1.6 kilometer, we need to adjust 90%. So, I think if we can have the, animals within 1 kilometer, that'll be ideal. But, again, this is what we recommended based on the what USDA and the practice. This you can see from the table that if it's within 1 kilometer, that's the best. It seems that indicates that's the optimal. Did I answer that question? No, is it something that, you know, maybe I just misunderstood what the question is? Other questions? We will share the code once we finalize it, and then you can practice with the code to generate the stocking rate, and also maybe you can practice for other kind of, you know, animals or you know, livestock.
Dr. Chair, I have a question, actually.
Yes.
So the base map for this water distance mapping at Google Earth Engine, what was it taken MODIS and which year?
For the MODIS, we take that for each year, we calculate the water distance, because each year we have different water satellite imagery from water maps from satellite imagery. So if it's a drought year, then the distance will be a little bit longer. And for wet year, the distance will be shorter. So we did calculation for each of the years from 2000 to 2019.
Также, например, доктор Чи, спасибо, также спрашивали вопросы до этого, как получить вот эти карты, да, то есть они в общем доступе или их надо покупать?
It is publicly available. And in the code, I think Linda showed the code, and then some of the code, maybe later on we can have a discussion, but the code pointed out where that location is. So the Google Earth Engine has that information where we can download. It's publicly available. Here, water list. Here is water. So that's where you can see. So from JRC, and then that's where the water from 2001 and 2020. So it's all publicly available. You can download, or if you use the code, you don't have to download, but they are available for this calculations. Other questions?
Можно вопрос?
Sure.
Вопрос. Омбаев Абдирахман, Казнау. Значит, у меня такой вопрос. Вы в своих расчетах или в исследованиях учитываете результаты исследований казахстанских ученых? Например, Казахский научно-исследовательский институт животноводства и кормопроизводства в 15-17 годах разработали гис-карты по республике. Там, значит, как раз учитывали водные источники и пастбищное содержание сельскохозяйственных животных. Там все полностью были изучены. Этот вопрос вы, значит, рассматриваете или нет?
Thank you for the question. I think this is really wonderful news to me. So our estimation is based on the field work that Mark's group and the Cast Now group did the survey. So we did not have the information that from this the person who asked the question. We did not have that information available to us. So it would be really, really wonderful if we can compare the two estimates so that we can have a understanding or better knowledge of where we are off or where we are on the target. So in short answer is that we did not compare the two, but it would be really wonderful if we can. I suggest that we work together or maybe he can compare, we can generate the product. He said that's 2015 and 16. If that's the case, we can definitely give the data, the product we generated to him so that he can do a comparison. I would love to see that effort if possible.
Да, конечно, это возможно, поскольку я работаю сейчас в Казнауи, значит, и мы с вами будем общаться, я с Майрой работаю вместе. Значит, здесь вот насчет такого от расстояния водных ресурсов, значит, источников, по нашим расчетам, вот это раньше мы проводили, я, значит, работаю в науке около 50 лет, значит, раньше мы проводили такие исследования, там расстояние должно быть около от 3 до 5 километров для сельскохозяйственных животных Казахстана. Вот такие тоже есть расчеты. Надо посмотреть.
Yes, we had Mark and Steve Papke and others. We had a discussion and saw some papers suggesting that animals travel maybe 7 or 8 kilometers. And as Mark explained, our estimate is optimal or is the ideal for best management. It does not necessarily mean that animals wouldn't travel longer distance. If they have to, they will. But it's a optimal estimation or a suggestion from our end. So definitely this is something we need to work on. Another thing, if CAS now had some of the information, I would like to suggest that keep one other thing in mind. When we estimate the water distance to the livestock, we used the water bodies that we see from satellites. But that doesn't include any whales that ranchers can use. I know some whales exist in Kazakhstan. So if you have wells and then you withdraw water and provide the water in maybe on a ranch or other places, that part we did not include in our estimate. So that is probably a potential area for uncertainty or error.
And Chi, the two other areas that we did not have direct information on is, and we did see it in Kazakhstan, is that in certain circumstances, they will actually truck water out to an area and put it in water troughs. So that's another area of reducing that distance of travel that we did see utilized. And then the second aspect then is it is possible to pipe water from a water source to another area and distribute it through your pastures at different watering points. And that's often used here in the deserts in the United States, where we'll use piping water from a spring source distribute it across the pasture. And then during the growing season, you can turn water on and off and move your cows so they don't stay in one area too long. And those are refinements that we don't have access to that information and needs to be adjusted for if you're doing an individual ranch plan.
That's exactly right. And also that, is an area of is maybe uncertainty, but also provide a management possibilities to graze more, livestock more efficiently. Other questions or comments?
Да, еще есть вопрос от Айгуль Бекбаевой. Учитывалась ли густота растительности?
Let me comment first, and then Mark may have better information. So for the vegetation density, I believe on the satellite imagery, when we estimate the NPP, that is part of this consideration. If you have a denser, more vegetation coverage, NPP should be higher. So I think NPP product derived from remote sensing or MODIS image does have that vegetation density information. But I don't know for sure if we have that considered, on the ground measurement. Mark, maybe you want to, you can comment?
Sure. If we define density as number of plants per unit area, then we have an inference to that in our line point intercept measurements on how many plants we hit as we go across that 100-meter transect. But she is correct. If we define density then using a slightly different interpretation, meaning the amount of standing biomass per meter square, if that's what we're actually the question is asked, then that was directly measured with our clipping studies, and that is then available to validate the remote sensing information, which ultimately its goal is to produce standing biomass in kilograms per hectare. And then we discount some of that vegetation if it's non-forage for beef cattle. So hopefully I answered your question.
Any other comments? This is really a wonderful discussion. We learned a lot.
I'm sorry, that one was in Russian. Hopefully it could get rephrased in English and then she and I could answer it.
And if there are no further questions, I think, we can go back and look at what we produced, and then maybe the group can start, looking at and download some of the product or the estimates. Keep in mind, though, that Mark and I, will continue working on this. And we will probably, revise some of this, the parameters or whatever based on, the field estimate, and then provide a final product or final code for the group to practice or to use for their own purpose. I think we will put a report out, shortly after we finish the project. Another thing, I think maybe Mark, if you want to comment or make an announcement, but we are, at least from my mind, we are planning to go back to Kazakhstan by sometime this fall, as soon as possible, so that we can work with Gunas, Mara, and others to do another round of field survey, not only just looking at the total amount of the forage and number of animals, but also we'll have a kind of understanding how people manage and where do they provide feeding materials, or how many days they feed in the winter time, etc. So we'll have a field trip to better understand the grazing system, and that would help us to better estimate the stocking rate and then develop some, maybe even some scenarios. What can we do to maximize the resource, the utilization, while protecting the environment?
Yes, Chi. Right now, we have hypothetical plans so that our team out of Kaz now would hopefully go out around mid-June to selected points on the satellite imagery where we have questions, and do some independent validation data collection. That'll then be sent here to the United States for Chi and I and our team to analyze, so we can refine uncertainty. That's all pending availability of local Kazakhstanians on our team to travel based on pandemic requirements in the country. And then Chi and I and our team would hope to come back late October, early November for approximately 2 weeks, then to refine everything with our CosNow partners, make a presentation to the Ministry of Agriculture on what we've learned to date. If they have questions or have uncertainty, we would have time then to make adjustments in the final report, which is due basically around the 1st of December. So that's kind of our travel plans, but it's all subject to availability of travel, both from the U.S. team to go into Kazakhstan, and our Kazakhstanian team's ability to travel from Almaty, then up to Akmola Oblast. The last thing then, and she mentioned it, but I just want to reiterate that what he presented today was really grazing potential during the grazing season, which we have roughly defined right now as 210 days. For the livestock production cycle for beef cows, there are really 3 components. So a major component is during that grazing season, which runs sometime in April to maybe sometime in October, depending upon the weather that year. Then you have, that's phase 1. Then phase 2 in the livestock production cycle is that winter confined area, where then there has to be forage provided to the livestock at their home ranch. So that would include primarily dry land hay, we believe. And then the third component then is the feedlot. So raising the livestock really has no value unless you sell them. And so then those calves move from the ranch to the feedlot. And they could be in the feedlot up to about 180 to 200 days, depending upon the weight that they enter the feedlot, the weight they want to be slaughtered at the feedlot, and then their daily average gain in weight. And so you have 3 components of forage or feed that has to be calculated for the beef cattle livestock production cycle. So what Dr. Chi is showing here is all the calculations necessary to fulfill that need during that grazing cycle, that spring, summer, early fall grazing cycle. When we talk next week, we'll go through then the confinement period and also then a brief discussion of the feedlot, so that the total forage required to produce, an animal for slaughter then can be calculated for the Ministry of Agriculture, so they know the resource demand for that entire cycle.
Dr. Chi, there is one question for actual Lin too. I will be fine with asking, code is not opening due to not having shape files. Can you send the visited site? So actually the Lin is also answering for the running code, the user should have the shape files, farm size and Akmula boundary uploaded to their own GEE account. So how should they upload this GEE account and how should we process that?
Okay, that's a good question. I think, we will provide that. We can send you the shape file or make the shape file available. And if anyone wants to do that, and then I will ask Linda to write just a brief instruction how to upload that shape file to the Google Earth engine. So maybe she said she can share the shape file later. So that will be available. And maybe Linda, you can also write a short, kind of instruction how to upload the shape file to their working environment.
Dr. Chi, I think we have the instructions and the report, the written one before about the basics of the Google Earth engine. But I can find the document and share it with the group.
Yeah, I think sent to Mara and Gunas. I think that the two are kind of facilitating. Okay. Other things that we need to discuss, I think we will have that code and the shape file sent to everybody. And then maybe, as people start practicing or running the code, having questions, I'm sure we can continue the conversation and we will be happy to answer some any questions you may have.
Okay, Dr. Chi, you actually can send all these instructions prepared with Lin and shape files to me, and I can share that with all the participants so that they try it before the next seminar starts, like on next Wednesday, and they try it and then give us the feedback. If that works?
Sure, that'll be good. And also, I think, if CAS now have that, livestock, stocking rate estimates for 2015 and 16, it would be really neat if they can run this for those 2 years and then compare with their assessment, just to get a better understanding and where we might be off. Again, this is a methodological training just to show how we can calculate. And then there are a lot of other factors, environmental factors, all the species information, etc. So that those need to be considered in the in the final calculation of stocking rate. There is a question, does NPP include productivity? Yes, it does. It's basically all the kind of, accumulated total biomass that is grown or accumulated over a year period of time. any other questions? So maybe, you know, if not, then we can adjourn this training, and we'll continue. I believe next week, Mark will talk about other, you know, considerations for sustainable management of livestock, particularly on the you know, protecting the environment, you know, soil erosions and others, sustainable management.
Спасибо, до свидания. Goodbye. До свидания. Было очень интересно.
Okay, well, thank you. Thank you so much. And thank you.
Вам тоже спасибо.
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 Thank you very much.
You're welcome.